When we talk about temperature in everyday life, we think of it as something that can always be increased. We heat water until it boils, metals until they glow, and stars until they shine. In daily experience, temperature feels like an open-ended scale. There is always something hotter. A flame hotter than boiling water. A furnace hotter than a flame. The sun hotter than a furnace. This intuition makes one idea feel natural. There should be no ultimate upper limit to temperature. But modern physics quietly tells a very different story. Just as there is a coldest possible temperature, absolute zero, there also exists a deepest and most extreme upper limit, a temperature beyond which the very meaning of space, time, and energy begins to dissolve. To understand why such a limit exists, we must begin with what temperature actually is. Temperature is not a substance, nor is it energy itself. It is a measure of how energy is distributed among the microscopic constituents of a system. In a gas, temperature reflects how fast the molecules move on average. In a solid, it reflects how strongly atoms vibrate around their fixed positions. In radiation, temperature is linked to the energy of photons and how densely they fill space. In every case, temperature is a statistical concept, emerging from enormous numbers of particles interacting according to the laws of physics. At low temperatures, these particles move slowly and behave in ways that often align with classical intuition. As temperature increases, particles move faster, collisions become more violent, and new physical effects appear. Materials change phase, chemical bonds break, atoms ionize into plasmas, and radiation becomes increasingly energetic. But even here, nothing seems to forbid temperature from rising without limit. Classical physics, in fact, once assumed that temperature could increase endlessly. The first cracks in this assumption appeared at the end of the 19th century. Physicists studying hot objects noticed something deeply troubling. When matter is heated, it emits electromagnetic radiation. The hotter it gets, the more radiation it emits, and the higher the typical frequency of that radiation. Classical theory predicted that as temperature increased, objects should emit infinite energy at high frequencies. This absurd prediction became known as the ultraviolet catastrophe. According to classical reasoning, there was no limit. Hotter meant endlessly more energetic radiation, without bound. Reality disagreed. Experiments showed that radiation from hot objects followed a very specific curve. Energy did increase with temperature, but only to a point for each frequency. High-frequency radiation was suppressed. The universe itself seemed to enforce a limit on how energy could be distributed. In 1900, Max Planck resolved this crisis by proposing something radical. Energy is not continuous. It comes in discrete packets, later called quanta. This single idea marked the birth of quantum mechanics, and it quietly planted the first seed of a maximum temperature. Quantum theory tells us that energy levels are quantized. Particles cannot absorb or emit arbitrarily small or arbitrarily large amounts of energy in a continuous way. As temperature rises, particles occupy higher energy states, but those states are structured. You cannot simply pile infinite energy into a system without changing the nature of the system itself. At extremely high temperatures, new degrees of freedom appear. Particles that once behaved independently begin to merge, transform, or lose their identity entirely. As temperature climbs beyond the scales of chemistry, atoms no longer survive. Electrons are stripped from nuclei, forming plasma. At even higher temperatures, nuclei themselves break apart. Protons and neutrons dissolve into a hot soup of quarks and gluons, similar to the state of the universe microseconds after the Big Bang. Each step upward in temperature corresponds to a deeper layer of physical structure being erased. This is already a clue. Temperature is not just about motion, it is about structure. Heating a system is, in a sense, an act of destruction. You are breaking patterns, symmetries, and organized forms. But there's only so much structure to destroy. Eventually, you reach a regime where the known building blocks of reality no longer make sense as separate entities. Yet even this does not fully explain a maximum temperature. One might imagine continuing indefinitely, heating this primordial soup further and further. To see why that fails, we must turn to relativity. Einstein's special relativity tells us that energy and mass are equivalent. As temperature increases, energy density increases. Enough energy packed into a small enough region of space will curve space-time itself. Gravity is no longer negligible. At ordinary temperatures, gravity plays no role in thermodynamics. At extreme temperatures, it becomes dominant. As energy density rises, the system begins to approach a critical threshold. Beyond this threshold, adding more energy does not merely make things hotter, it causes space-time to collapse. The energy itself becomes trapped behind an event horizon. Instead of raising temperature, you create a black hole. This insight leads us to a remarkable conclusion. There exists a temperature at which the energy required to make a system hotter inevitably forms a black hole first. Beyond this point, the concept of temperature loses meaning because temperature assumes a system that can exchange energy with its surroundings. A black hole isolates that energy behind a horizon. The universe refuses to let temperature increase further in any operational sense. This limiting temperature is known as the Planck temperature. It is approximately 1.4 times 10 to the 32 Kelvin. This number is unimaginably large. It is far hotter than the core of any star, hotter than supernovae, hotter than the early universe a fraction of a second after the Big Bang. It is a temperature so extreme that all known forces, electromagnetism, the weak force, the strong force, and gravity, are expected to merge into a single unified interaction. The Planck temperature is defined not by experimental measurement, but by fundamental constants: the speed of light, Planck's constant, Boltzmann's constant, and Newton's gravitational constant. This is crucial. It means the maximum temperature is not a property of matter, but a property of space-time itself. It arises from the structure of the universe at the deepest level. At this temperature, quantum mechanics and general relativity are equally important. Our current theories cannot fully describe this regime. Space and time themselves are expected to fluctuate violently. Distances lose meaning. Causality becomes uncertain. The smooth fabric of space-time dissolves into a quantum foam. Importantly, this does not mean that the universe ever truly reached or exceeded this limit in a conventional sense. Even during the Big Bang, physics as we know it breaks down before this limit is reached. The Planck temperature marks not a physical state we can describe, but a boundary beyond which our concepts fail. This brings us to a subtle but profound point. The maximum temperature of the universe is not a temperature in the same way boiling water has a temperature. It is a limit to description. It tells us where our language of particles, fields, and space-time stops being meaningful. Asking what happens above this limit is like asking what lies north of the North Pole. The question itself loses coherence. Yet this limit has real consequences. It shapes our understanding of the early universe, black hole physics, and the unification of forces. It tells us that the universe is not infinitely permissive. There are boundaries, not imposed arbitrarily, but emerging from the deep consistency of physical law. To move further, we need to confront a subtle idea that often goes unnoticed. Temperature is inseparable from entropy. In everyday terms, entropy is often described as disorder, but in physics it has a much more precise meaning. Entropy measures the number of microscopic configurations that correspond to a macroscopic state. When temperature rises, entropy almost always rises with it, because higher energy allows particles to arrange themselves in more possible ways. At low temperatures, systems are constrained. Atoms vibrate gently, particles occupy low-energy states, and there are relatively few ways to rearrange the system without changing its overall appearance. As temperature increases, constraints loosen. Particles explore larger regions of phase space. Entropy grows. But entropy cannot grow arbitrarily without consequence. The relationship between energy, entropy, and temperature is encoded in a simple but profound equation. Temperature is the rate at which entropy changes with energy. When adding energy greatly increases the number of available states, temperature is low. When adding energy barely increases the number of states, temperature becomes extremely high.
This leads to an important insight. A maximum temperature corresponds to a regime where adding more energy does not meaningfully increase entropy. The system has, in a sense, run out of new configurations to explore. At that point, temperature ceases to be a useful concept. In conventional matter, this saturation never occurs. There are always new excitations, new particles, new modes of motion. But when gravity enters the picture, entropy behaves very differently. Black holes, surprisingly, possess entropy, and it is enormous. The entropy of a black hole is proportional not to its volume, but to the area of its event horizon. This discovery, made by Jacob Bekenstein and Stephen Hawking in the 1970s, revolutionized our understanding of thermodynamics. Black hole entropy grows faster with energy than the entropy of any ordinary system. This means that at sufficiently high energy densities, the most entropic configuration of matter is not a hot gas or plasma, but a black hole. Nature prefers black holes when pushed to extremes. This preference has deep implications. Suppose you try to create a system with a temperature exceeding the Planck temperature by injecting more and more energy into a region of space. As you do this, entropy rises until it becomes entropically favorable for that region to collapse into a black hole. When this happens, the system reorganizes itself into a fundamentally different state. The degrees of freedom you were heating no longer exist as independent entities. They are replaced by a horizon. At that point, temperature becomes ambiguous. A black hole does have a temperature, the Hawking temperature, but paradoxically, it is inversely proportional to its mass. The more energy you add, the colder the black hole becomes. This is the opposite of ordinary matter. Adding energy no longer raises temperature, it lowers it. This inversion is not a curiosity, it is a warning. It tells us that beyond a certain point, the intuitive link between energy and temperature breaks down completely. The Planck temperature marks the boundary where thermodynamics as we know it gives way to something more fundamental. Another way to see this limit is through length scales. Temperature can be associated with a characteristic wavelength. Hotter systems correspond to shorter wavelengths, higher frequencies, and finer spatial structure. As temperature increases, the relevant wavelengths shrink. But there is a smallest meaningful length in physics, the Planck length, about 1.6 times 10 to the minus 35 meters. Trying to probe structures smaller than this length requires energy so high that space-time itself collapses. Once again, gravity intervenes. The attempt to localize energy on extremely small scales leads inevitably to black hole formation. Thus, the Planck length and the Planck temperature are two sides of the same coin. One limits how small space can be meaningfully divided. The other limits how much thermal energy can be meaningfully concentrated. Time, too, is implicated. High temperatures correspond to rapid processes, short timescales, and violent fluctuations. The Planck temperature is associated with the Planck time, roughly 5.4 times 10 to the minus 44 seconds. Below this timescale, the concept of temporal order becomes fuzzy. Cause and effect blur. The notion of a smooth flow of time may simply not exist. At this depth, temperature stops being about particles moving faster. Instead, it becomes a statement about how violently space-time itself fluctuates. Near the Planck temperature, space-time is no longer a passive stage on which physics plays out. It becomes an active participant, jittering, branching, and rearranging. Quantum field theory, which successfully describes particles and forces at high energies, assumes a fixed space-time background. General relativity, which describes gravity, assumes space-time is smooth and continuous. Near the Planck temperature, both assumptions fail simultaneously. We do not yet possess a complete theory that unites them. Candidate frameworks such as string theory and loop quantum gravity attempt to describe this regime, but none are experimentally verified. What they agree on, however, is the existence of a fundamental cutoff. Whether space-time is made of vibrating strings, discrete loops, or something even more abstract, there is a smallest unit of structure and a corresponding maximum energy scale. Temperature cannot exceed this scale without dissolving the very framework needed to define it. This casts the early universe in a new light. The Big Bang is often imagined as an infinitely hot singularity, but modern physics strongly suggests this picture is misleading. The universe did not begin at infinite temperature. Instead, it emerged from a regime where our descriptions fail. The Planck temperature marks the edge of what we can meaningfully say, not necessarily a physical peak that was ever attained. This distinction matters. Infinite temperature would imply infinite energy density, infinite entropy, and infinite curvature, conditions that destroy predictability. A maximum temperature, by contrast, preserves consistency. It tells us that the universe has built-in safeguards against infinities. Interestingly, this idea echoes across physics. The speed of light is a maximum speed. Absolute zero is a minimum temperature. The Planck temperature is a maximum temperature. These limits are not arbitrary. They arise from the deep structure of physical law, from the way information, energy, and causality are intertwined. Information theory provides yet another perspective. Temperature is linked to information content. A hotter system encodes more uncertainty about the precise state of its constituents. But there is a maximum amount of information that can be stored in a given region of space, again proportional to area, not volume. This is known as the holographic principle. It suggests that the universe fundamentally limits how much information, and therefore how much entropy and temperature, can exist in a region. When this informational bound is saturated, adding more energy does not increase temperature. It merely changes how information is encoded, often by creating horizons. Temperature, entropy, gravity, and information converge into a single story. At this point, we are forced to reconsider what we mean by hot. Near the Planck temperature, there may be no particles, no fields, no space-time in the usual sense. There may only be raw degrees of freedom exchanging information in ways we do not yet understand. Calling this a temperature may be a linguistic convenience rather than a literal description. Yet the limit remains meaningful. It shapes the boundaries of all physical processes. It tells us that the universe is not infinitely malleable. There's a deepest layer beyond which questions lose their footing. And from here, the implications become even stranger, because once temperature reaches its maximum meaningful value, the distinction between thermal motion and quantum uncertainty begins to disappear. At the deepest level, temperature is inseparable from uncertainty. In quantum mechanics, uncertainty is not a flaw in measurement, it is built into reality itself. Heisenberg's uncertainty principle limits how precisely certain pairs of quantities can be known simultaneously. Energy and time form such a pair. The more precisely energy is defined, the less precisely time can be defined, and vice versa. At extreme temperatures, energy fluctuations become so violent that time itself becomes uncertain.
Near the Planck temperature, fluctuations in energy over extremely short timescales are comparable to the total energy content of the system. This means that space-time geometry itself fluctuates. The idea of a fixed background on which thermal motion occurs no longer applies. Temperature, which relies on averaging over time and over many particles, loses its statistical foundation. This brings us to a quiet but profound realization. Temperature assumes equilibrium. A system must have enough time to explore its available states and settle into a statistical distribution, but at Planck scale energies, the characteristic time scale is the Planck time. There may be no meaningful sense in which equilibrium can be established. Without equilibrium, temperature is undefined. In this sense, the maximum temperature is not enforced by a wall, but by a collapse of meaning. The universe does not forbid higher temperatures in the way a solid wall forbids motion. Instead, it dissolves the concepts required to define temperature at all. This perspective aligns with modern views of quantum gravity. In many approaches, space-time is emergent rather than fundamental. It arises from deeper, non-spatial degrees of freedom. Temperature, too, may be emergent. It may exist only when space-time has already taken on a classical, smooth form. Above the Planck scale, both space-time and temperature evaporate as useful ideas. String theory provides an illustrative example. In string theory, particles are not point-like objects, but extended objects with a characteristic length. Heating a system in string theory eventually excites longer and longer strings rather than creating higher energy point particles. At a certain temperature, known as the Hagedorn temperature,
Adding energy does not increase temperature. It produces more massive strings instead. Temperature plateaus. Although the Hagedorn temperature is not identical to the Planck temperature, the lesson is similar. Nature resists unlimited heating by redirecting energy into new forms of structure. Temperature saturates, not because energy stops flowing, but because the way energy manifests changes. Loop quantum gravity tells a different story, but reaches a comparable conclusion. In this framework, space itself is quantized. Areas and volumes come in discrete units. This discretization implies a finite number of degrees of freedom in any region of space. Finite degrees of freedom mean finite entropy. Finite entropy implies a maximum temperature. Across these theories, the message is consistent. The universe has a built-in ultraviolet cutoff. It is not an accident, it is required for consistency, stability, and predictability. One of the most unsettling implications of a maximum temperature concerns the arrow of time. The arrow of time is usually associated with increasing entropy, but if entropy has an upper bound in a given region, then the arrow of time may lose its direction near that bound. Time may not flow in the way we imagine at the earliest moments of the universe. Some cosmological models suggest that the universe emerged from a state of minimal entropy rather than maximal temperature. Others suggest a bounce rather than a beginning. In many of these models, the Planck temperature acts as a regulator, preventing singularities and infinities. The universe never becomes infinitely hot. Instead, it transitions through a phase where our classical concepts are replaced by something deeper. Even black holes reflect this logic. As a black hole evaporates through Hawking radiation, its temperature rises. Smaller black holes are hotter. But if evaporation continued indefinitely, the temperature would diverge. Many physicists suspect that evaporation halts at the Planck scale, leaving behind a remnant or transitioning into a new phase. Once again, the Planck temperature appears as a boundary, not to be crossed, but to be approached asymptotically. All of this forces us to confront a humbling truth. The maximum temperature of the universe is something we can't create, measure, or even fully imagine. It is a signpost pointing to the edge of knowledge. It marks the point where physics stops being a story about things moving in space and becomes a story about the emergence of space itself.
Near the Planck temperature, fluctuations in energy over extremely short timescales are comparable to the total energy content of the system. This means that space-time geometry itself fluctuates. The idea of a fixed background on which thermal motion occurs no longer applies. Temperature, which relies on averaging over time and over many particles, loses its statistical foundation. This brings us to a quiet but profound realization. Temperature assumes equilibrium. A system must have enough time to explore its available states and settle into a statistical distribution. But at Planck-scale energies, the characteristic timescale is the Planck time. There may be no meaningful sense in which equilibrium can be established. Without equilibrium, temperature is undefined. In this sense, the maximum temperature is not enforced by a wall, but by a collapse of meaning. The universe does not forbid higher temperatures in the way a solid wall forbids motion. Instead, it dissolves the concepts required to define temperature at all. This perspective aligns with modern views of quantum gravity. In many approaches, space-time is emergent rather than fundamental. It arises from deeper, non-spatial degrees of freedom. Temperature, too, may be emergent. It may exist only when space-time has already taken on a classical, smooth form. Above the Planck scale, both space-time and temperature evaporate as useful ideas. String theory provides an illustrative example. In string theory, particles are not point-like, but extended objects with a characteristic length. Heating a system in string theory eventually excites longer and longer strings rather than creating higher energy point particles. At a certain temperature, known as the Hagedorn temperature, adding energy does not increase temperature. It produces more massive strings instead. Temperature plateaus. Although the Hagedorn temperature is not identical to the Planck temperature, the lesson is similar. Nature resists unlimited heating by redirecting energy into new forms of structure. Temperature saturates not because energy stops flowing, but because the way energy manifests changes. Loop quantum gravity tells a different story but reaches a comparable conclusion. In this framework, space itself is quantized.
Areas and volumes come in discrete units. This discretization implies a finite number of degrees of freedom in any region of space. Finite degrees of freedom mean finite entropy. Finite entropy implies a maximum temperature. Across these theories, the message is consistent. The universe has a built-in ultraviolet cutoff. It is not an accident. It is required for consistency, stability, and predictability. One of the most unsettling implications of a maximum temperature concerns the arrow of time. The arrow of time is usually associated with increasing entropy, but if entropy has an upper bound in a given region, then the arrow of time may lose its direction near that bound. Time may not flow in the way we imagine at the earliest moments of the universe. Some cosmological models suggest that the universe emerged from a state of minimal entropy rather than maximum temperature. Others suggest a bounce rather than a beginning. In many of these models, the Planck temperature acts as a regulator, preventing singularities and infinities. The universe never becomes infinitely hot. Instead, it transitions through a phase where our classical concepts are replaced by something deeper. Even black holes reflect this logic. As a black hole evaporates through Hawking radiation, its temperature rises. Smaller black holes are hotter, but if evaporation continued indefinitely, the temperature would diverge. Many physicists suspect that evaporation halts at the Planck scale, leaving behind a remnant or transitioning into a new phase. Once again, the Planck temperature appears as a boundary, not to be crossed, but to be approached asymptotically. All of this forces us to confront a humbling truth. The maximum temperature of the universe is not something we can create, measure, or even fully imagine. It is a signpost pointing to the edge of knowledge. It marks the point where physics stops being a story about things moving in space and becomes a story about the emergence of space itself. And yet, this limit is not restrictive in a negative sense. It is enabling. Without a maximum temperature, the universe would be unstable. Energy could concentrate arbitrarily, destroying structure at every scale. The existence of stars, galaxies, chemistry, and life depends on the fact that the universe has limits. As we push closer to that limit in our theories, we find that the question, how hot can the universe get, quietly transforms into a deeper question. What must the universe be like in order for anything at all to exist?
To go further still, we have to let go of the idea that temperature is a fundamental quantity at all. In the deepest formulations of physics, temperature is not primary. It emerges from more basic concepts, such as information flow, entanglement, and coarse graining. What we call heat may simply be the macroscopic shadow of microscopic ignorance. In quantum systems, entropy is closely tied to entanglement. When a system becomes highly entangled with its environment, its internal state appears thermal, even if the combined system is in a pure quantum state. This suggests that temperature may arise not from randomness, but from correlations. At extreme energy scales, entanglement becomes so strong and so pervasive that separating system from environment may no longer be meaningful. Near the Planck temperature, everything is entangled with everything else. There may be no meaningful subsystems to assign temperatures to. Without separability, thermodynamics collapses. The maximum temperature is therefore not a limit on energy, but a limit on separability. This idea resonates with the holographic principle. According to this principle, all the information contained in a volume of space can be described by degrees of freedom living on its boundary. In such a universe, heating a region does not increase the number of internal degrees of freedom indefinitely. Once the boundary is saturated, the interior cannot become hotter in any conventional sense. From this viewpoint, the Planck temperature corresponds to a state where the holographic bound is saturated everywhere. Space is maximally packed with information. Any additional energy must reorganize information rather than increase temperature. Horizons form, geometry reshapes, but temperature stagnates. This reframing also sheds light on why gravity is so deeply connected to thermodynamics. Einstein's equations, when examined carefully, can be rewritten in a form that resembles thermodynamic relations. Space-time curvature behaves like an equation of state. In this picture, gravity is not a force, but an emergent phenomenon arising from underlying statistical behavior.
If gravity itself is thermodynamic in origin, then the existence of a maximum temperature becomes almost inevitable. When the microscopic degrees of freedom responsible for spacetime reach saturation, spacetime resists further heating. It stiffens, not unlike a material reaching its elastic limit. Beyond that point, adding energy changes the phase rather than the temperature. There are hints of this behavior even at lower energies. In certain condensed matter systems, temperature increases until a phase transition occurs. Beyond that transition, temperature can remain nearly constant while energy continues to flow into restructuring the system. The Planck temperature may represent a universal phase transition of spacetime itself. Another path to this conclusion comes from thought experiments involving particle collisions. As collision energies increase, we expect to probe smaller distances, but beyond a certain energy, collisions no longer resolve finer structure. Instead, they produce black holes. The cross-section grows with energy, resolution worsens rather than improves. High energy ceases to reveal small scales, it hides them. This phenomenon, sometimes called classicalization, implies that extreme energy does not grant access to arbitrarily high temperatures. Instead, it triggers macroscopic gravitational behavior. Temperature is diverted into geometry. This inversion challenges a deeply ingrained intuition that higher energy always means finer detail. In a universe with gravity, the opposite can be true. At the highest energies, the universe becomes coarse rather than fine. The maximum temperature marks the turning point where adding energy no longer sharpens reality but blurs it. Even the vacuum is affected. At ordinary temperatures, the vacuum appears empty. At high temperatures, it becomes a seething foam of virtual particles. Near the Planck temperature, the distinction between vacuum and matter dissolves. The vacuum itself carries entropy, temperature, and information. Heating the vacuum further becomes meaningless because there is nothing left to excite. This suggests that the maximum temperature is not associated with matter at all, but with the vacuum structure of spacetime. It is the temperature of existence itself. Cosmology reinforces this picture. Inflationary models propose that the early universe underwent a rapid expansion driven by vacuum energy. During this phase, temperature is not well defined in the usual sense. Thermal equilibrium does not exist. The universe is dominated by a field configuration rather than a hot plasma. The Planck temperature again appears not as a realized state, but as a boundary separating thermal and pre-thermal physics. As we move deeper into this regime, the language of particles, fields, and even dimensions begins to fail. Some theories suggest that dimensions themselves may change at energy scale. Space may become effectively lower dimensional near the Planck scale. If dimensionality is not fixed, then temperature, which depends on the density of states, must also change character. In fewer dimensions, the growth of entropy with energy is slower. This naturally limits temperature. Once again, the universe finds a way to cap extremes by altering its own structure. At this depth, the maximum temperature is no longer a number, it is a condition, the point at which description gives way to emergence, where thermodynamics, geometry, and information merge into a single, indistinguishable concept. At the deepest level we can currently glimpse, the idea of a maximum temperature is inseparable from the idea that reality has a finite capacity for distinction. Temperature, entropy, and information are all different languages describing the same limitation. The universe can only meaningfully differentiate states up to a certain point. Beyond that, distinctions blur faster than they can be defined. One way to see this is through the density of states. In ordinary systems, the number of accessible states grows rapidly with energy. That growth is what allows temperature to increase smoothly. But when gravity is included, the growth of states changes character. Black holes dominate the high-energy spectrum. The number of states no longer grows freely with volume, but is constrained by area. This fundamentally alters thermodynamics. If the number of possible states grows too slowly compared to energy, temperature must diverge. But instead of allowing divergence, the universe reorganizes itself so that the assumptions behind temperature no longer apply. The system ceases to be describable as a collection of distinguishable microstates evolving in time. The statistical foundation collapses before temperature can exceed its bound. This suggests that the Planck temperature is not a hottest state, but the temperature associated with the last meaningful statistical description of reality. It is the temperature of the final, coarse-grained description before the universe becomes fine-grained beyond comprehension. From this viewpoint, the Planck scale represents a kind of epistemic horizon. Just as the event horizon of a black hole limits what can be observed, the maximum temperature limits what can be meaningfully described. Physics does not end there, but our current frameworks do. Even causality becomes suspect. Temperature presumes temporal ordering. Energy exchanges occur, systems equilibrate, averages stabilize. Near the Planck regime, space-time fluctuations are so extreme that causal order may not be well defined. Events may not admit a consistent before and after description. Without causality, equilibrium cannot exist. Without equilibrium, temperature evaporates as a concept. This reframes the Big Bang itself. Rather than an infinitely hot origin, the universe may have emerged from a phase where temperature was undefined. Cooling did not begin from infinity, but from the moment when space-time became classical enough for thermodynamics to apply. The maximum temperature marks the birth of temperature itself. Seen this way, the universe did not begin hot and cool down. It began indescribable and only later became hot. This interpretation resolves many long-standing paradoxes. It avoids singularities, tames infinities, and explains why every attempt to exceed these limits, whether by compressing energy, probing smaller distances, or accelerating particles, results not in greater intensity, but in concealment. Horizons form, resolution degrades, information spreads out rather than concentrate. The universe protects its own coherence. What began as a simple question, how hot can the universe get, has quietly transformed into a statement about the architecture of reality. The maximum temperature is not imposed by matter, nor by technology, nor by human limitation. It is woven into the logic of existence. It arises because a universe capable of structure, memory, and continuity cannot allow unlimited concentration of energy without erasing itself. In that sense, the maximum temperature is not an extreme to be feared or challenged. It is a boundary that makes everything else possible. It is the silent condition that allows stars to burn without tearing space-time apart, allows the early universe to evolve rather than collapse, and allows physics itself to remain intelligible. Beyond that boundary, there may be deeper rules, deeper descriptions, and deeper forms of order. But temperature, as we understand it, belongs to this side of the divide, where space exists, time flows, and meaning can still be assigned. And that is why the universe has a maximum temperature, not because it runs out of energy, but because it runs out of ways to be different.